It is certainly a privilege and it's an honor to present a few of my ongoing research works and state of the art on hardware security and IP code protection. Uh, I would like to thank IEEE student branch of CEA Kerala section, which is region 10 of IEEE. Okay, so I'll move and I'll keep on talking about. Okay, so for most of my talks, I'm going to use the contents from my book. So these two are my recent books. In case if you wish to read more and understand more about the topics that I'm going to speak, please refer to these books, and you can procure them in one of your libraries as well. Okay, so what is a hardware security and how do we use it? So let me first say that when we talk of the word hardware security, it is very important to understand that what are the different types of hardware that we are referring to. There could be multiple classifications of a hardware. Hardware could be a combinational circuit, a hardware could be a sequential circuit, a hardware could be a computationally intensive block, which we often call as intellectual property block. A hardware could be a DSP hardware accelerator, which is responsible for accelerating data intensive tasks. So there are different classifications of hardware. So when we want to develop hardware security techniques, algorithms, or processes, very important right at the beginning is to understand what is the target platform. Okay. So in this talk, I would be focusing on the most complex hardware, which is the hardware accelerators or the reusable IP cores. And there are many real life applications of those that you see in everyday life. So one of those applications is what you see in the slide of a digital camera, which is a very well-known example of a consumer electronics device. So what I'm basically trying to put here and explain is in a digital camera, there are so many internal blocks that are available. So where is the security mechanism needed? So let's look into that. So just by converting an analog image that falls on the lenses of a camera and processed by something called CCD, which we call as charge coupled devices, into its corresponding digital data form, does not really create a digital image. So after it falls into the lens and it gets some processing done by CCD, it is then sent to the image processing blocks and then to the codec engine that performs variety of data calculations until when we see actually what a grayscale or a colored image is. So if you see this diagram at the bottom, the subject's image falls on the lens, which passes through the CCD lens. It goes through a to D converter, which produces a raw data of the image, and this raw data is then sent into the image processing engine, which is responsible for doing a lot of adjustments on the brightness, contrast, blurring, sharpening, so on the images, which of course can be done using hardware accelerator also. Followed by, then it goes on to one of the compression engines, which is very well known, which we call as JPEG codec or JPEG compression decompression engine. Or if you want to skip it, we can pass it through a TIFF, and then it finally gets stored after some compression algorithms in a memory card. So here the security can be applied in the compression engine, which is the block which we call as compression processing, or the security can be applied in the image processing engine. So that is the main essence of putting this diagram here, so that you know what is the target hardware that we're trying to secure or protect. Okay, let us look a little bit more into this. Now these blocks, they are mostly processing signals, 2D signals, or which we call as images, or 1D signals, which we know as audio signals. So these signals are usually processed by something called as DSP cores, digital signal processing cores. People from electronics background may have heard about it. So what this DSP core basically does is that it is acting as a second microprocessor beside the main microprocessor, which is responsible for checking the emails, managing your Wi-Fi, and doing the augment and accessibility works. But the main processor, which is actually responsible for processing the videos and the audios, is the DSP dedicated DSP block, because it is doing all the mathematical calculations which a normal microprocessor, if allocated, will consume a lot of time. So besides the main microprocessor, there is also a dedicated DSP block that you see available in a digital camera. One of the examples that you see in this figure is a Nikon XP, which is built as a SoC, which includes an image processor, video processor, DSP, 32-bit microcontroller, all laid down on a single platform. So this entire thing is part of a digital camera, and is to be secure. So this is just to show and give you an example of JPEG codec circuit that was built by one of my ex-PhD students. He's currently working as an assistant professor in IEEE. So this was one of part of his thesis work. This was a JPEG codec that is responsible for capturing the images and doing operation of it entirely through the hardware. The pixel values are the compressed pixel values of the image. And this is the JPEG codec that could be secured or that has been secured. One of the methods which I'll explain a little later, obfuscation. As you can see, you can even imagine the complexity of the application by looking at the JPEG codec structure. This is a JPEG codec at RTP level, and you can imagine that when convert that to a gate level structure or to a netlist, will become hugely. Another application of a DSP that needs to be secured is you see an MP3 encoder chain that is visible here. In this MP3 encoder chain, you can see there are several DSP blocks all together. The first one is a filter by modified DCT, which is another DSP block that is responsible for converting time domain to frequency domain or spatial domain to spectral domain. Then we have a quantization block, Hoffman encoding, and finally the bit stream. And also you have the Fourier transformation working in parallel with this. So this entire MP3 encoder chain has so many several DSP blocks that can all get affected by security threats and needs to be secure. Okay, a little bit more into the applications, then I'll get into the security threats that I'm referring to. So as I was saying, hardwares could be of different types. One of the other applications is known as hardware accelerators for popular DSP and image processing applications. Now this hardware accelerator, some of the famous applications, or I would say profound well-known applications in real life, could be a finite impulse response filter. Again, people from electronic background who have studied about signal processing who know what I'm referring to. FIR is a very well-known filter that is responsible for doing processing of the incoming signal. Okay, so it often has a feed-forward path but no feedback. Okay. The second one is known as JPEG compression decompression, which I just gave an example. This is used in image processing and inside a digital camera. Very well known. Third is a convolution filter. So this convolution filter is also very important. They are responsible for image processing and image manipulations at the hardware level. So they can be again of the following four types. Again, there could be many others, but I've just put the four most important convolution filter, which is image blurring filter, responsible for blurring the images. Second is the image sharpening filter. What it does, it sharpens certain aspects of the image once you feed it into the hardware. Image embossing filter, so it could be vertical embossment or horizontal embossment. And finally, the image edge detection filter that highlights the certain edges of the image. So they all are part of the convolution filter, and they can all be done directly at the hardware level. And this hardware again needs to be secured against external hardware threats. The fourth application is Fourier transform. This is again a little bit like DCT, responsible for converting spatial domain to spectral domain, and they can again be useful in many applications such as spectral analysis, frequency response analysis, and so on. And finally, we have the discrete cosine transform. This is again used in JPEG compression for processing 8% image blocks. Okay, now let me get into some of the well-known security techniques, algorithms, and modules that are used or that have been proposed in the state-of-the-art literature as well as used in the industry. So they are pretty much the state-of-the-art technologies that you see in today's world and yet to come in the circuits. So first is a crypto stability. This is again for protecting the IP ownership of a genuine owner. They can also help in securing and protecting against IP piracy and IP counterfeiting. I'll explain a little later what those piracy and counterfeiting means. Second is integrated watermarking and key-based structural obfuscation. This is a bit of a dual line of defense technique that is used for both preventive control and detective control against threats of IP ownership and reverse engineering. The third is a biometric fingerprint. This is certainly very exciting field. We have recently done this work in our lab with one of my PhD students, and we are exploring the ability of hardware, securing a hardware IP using biometric fingerprint. That's one of the most important things. The fourth technique that you see is known as integrated cryptosteganography and structural obfuscation. In this, what we have done basically is that we have again used double line of defense to secure a given piece of hardware from piracy, counterfeiting, and cloning, as well as we have employed certain modifications to the hardware circuit so that it becomes a little unobvious for an attacker to launch reverse engineering attack on it. Okay, so obfuscation prevents reverse engineering, and cryptosteganography prevents or detects rather passive mode of detection against IP ownership and piracy. And finally, we have key-based hash chaining. This is another algorithm. It is again used as a steganography technique, or could be used as a watermarking technique in order to implant digital evidence into your system so that nobody else can steal your hardware. We have also developed certain hardware security tools which are yet to be released. So we are planning for its public release in September 2020 of this year. And we are planning to release 4 different tools of 4 different hardware security threats. So first is the crypto stego tool, second is a KSO PW tool, third is a KHC stego tool, and fourth is a POM SO tool. They all are pretty much handling 4 major types of threat. The first is IP ownership abuse, so that whatever design you make that cannot be abused by a third party, attacker or adversary. Second is piracy, which includes cloning and counterfeiting that can again be secured using steganography and watermarking. And the next is reverse engineering that also leads to hidden insertion of Trojans into the hardware. So as long as you can prevent reverse engineering or you can hinder reverse engineering, what you're making sure is that insertion of Trojan becomes quite difficult. So these tools all can be used to design hardwares with inbuilt security properties. Okay, with inbuilt security properties, the tools would have complete readme instructions along with the tutorials that can be used by any user by following the guidelines. Okay, now let me get a little bit into the theory so that you can get more idea about what I'm talking about. So hardware security can again be broadly classified into 2 major types. First is authentication based approaches. Second is obfuscation based approaches. The second type of hardware security approach, which is obfuscation, can again be further subdivided into 2 types. The first is called structural obfuscation, where you will try to structurally obfuscate your design so that it becomes unobvious to a attacker. So what I'm trying to say basically is that if a particular hardware has a standard popular structure, then if you make the structure in some unobvious form without affecting the functionality, all that you're giving or ensuring the designer by making sure that the attacker will not be able to identify the structure of the hardware by inspecting the structure. Okay, so that's what structural obfuscation does. Okay, once the identity of the structure is visible, it can no longer help. Okay, so therein comes the second form of obfuscation, which is known as functional obfuscation. Many people also call this as logic locking. What this basically does is that it encrypts the circuit even if the structure becomes visible or known to an attacker. Logic locking or functional obfuscation will encrypt the circuit at the gate level so that only when you apply a certain valid key sequence, the structure becomes functional in the sense of giving the correct output. Okay, so both of these obfuscation techniques are known as active mode of protection, and they can certainly prevent or create a lot of obstacles and thwart against reverse engineering attacks. Okay, so this is a diagrammatic overview of what I'm talking of. Threats to an IP core could be ownership abuse, could be piracy, could be Trojan insertion, could be false claim of ownership. Again, these can again be handled with the use of digital watermarking. Another method which is quite popular is known as computational forensic engineering. It can again be tackled using IP metering, and it can also be tackled using logic and structural obfuscation. Okay, now IP protection of DSPs, that can be done using forensic detective control. Now, forensic detective control means we are actually trying to detect whether the given piece of hardware, is authentic or it is a forged hardware. Okay, by checking the authenticity, you can make sure that the hardware is genuine and it can be integrated in the SoC design chain. So, and also you can detect a pirated hardware by making sure that the authentic stego mark or watermark is there inside it or not. So therefore, we call it detective control. Why we have the word forensic at the beginning of it is that this is usually done in the forensic labs through the methods of forensic analysis, because the detection algorithm is also not straightforward. There are certain inputs and certain outputs that has to be digitally followed in order to make sure that it is able to detect the genuine mark right away. Now we have single phase hardware watermarking, we have multi-phase hardware watermarking, we could have multi-level hardware watermarking, and we can also have hardware steganography. So these four are pretty much similar in the way how it functions and how the algorithm works. But there's another method which is known as digital signature based watermark. This is a little different than the existing ones. In digital signature based watermark, what happens is we embed a digital signature into the hardware. Now, this digital signature is pretty similar to what you see in digital certification processes. The digital signature is derived from the hash followed by RSA encryption of the input design. Okay, I'll give an example. Okay, so before that, I'll also talk a little bit about what basic steganography model does. So hardware steganography, as I said, is also a very important method. You have an embedded block where you have a covered data of the design, and you have a stego key followed by the embedded data. So there are three inputs. So those three inputs along with the embedded block takes part in the stego encoder process. And once you derive the stego data, it then goes into the extractor block where you have again the stego key and you derive the embedded data. So if it matches, you know that there's a genuine data here. Okay, now moving forward, obfuscation, as I said, obfuscation could be of two types. One is the structural obfuscation, second is the logic obfuscation. So structural obfuscation, as I said, it tries to change the structure of the design without affecting the functionality. Some of the popular techniques that have been used in the literature and research and in the state of the art is compiler transformation based structural obfuscation. Second is high level transformation based structural obfuscation of fault secure DSP circuits. The third is hologram based structural obfuscation. And finally, we have the functional obfuscation of DSP circuits using logic locking and IP locking blocks. In the last category, we can also append other encryption circuits like AES and SHA and other lightweight solutions to thwart other types of attacks like SAT as well as removal attacks. Now let me give you a flow of a design flow of how you can embed this security algorithm. For people who are aware of VLSI, you may have heard of the word high-level synthesis. This is a very important flow for data-intensive hardware accelerators, and we use this framework for designing any DSP, any communication-based hardware accelerators, any image processing, multimedia-based hardware accelerators. So what we do is basically we will embed this digital evidence inside the HLS framework. Okay, while the design process is ongoing. So it's an in-synthesis design process, not neither pre nor post. It's in synthesis. While we do the designing, we will insert the hidden elements of the security protocol or algorithm within the design. Okay, so what are the inputs? So the primary inputs is of course a module library, which is a technology library of the cells. Then you have the DSP core, which is the application which you want to secure. So that can be processed through a DFG or a C code. A DFG is nothing but a data flow graph, a graphical representation obtained through a C code or from a C code. And then we can give some timing sequence, some timing specs, some area specifications and constraints, or power specifications and constraints also. Within the HLS framework, we have a DAC system. This DAC system is responsible for producing an optimal architecture of your design. And once you have the optimal architecture, you can process through the scheduling, hardware and register allocation, as well as binding. And the last two steps of producing multiplexing and data path controller will result into an RTL level circuit. This entire block steadily interacts with the hardware security framework that involves security algorithms as well as IP vendors' security information, such as the key constraints, etc. Okay, and once this thing is done by the in synthesis process, we may generate a gate level DSP circuit that can again be carried forward to the layout design. Okay, so this is another diagrammatic overview of the different types of hardware threads that needs to be taken care of. So the flow is from an IP vendor, which is usually a third-party IP vendor, followed by the SOC design house, where it goes for third-party IP integration, or we known as, or we call this as multi-vendor IP integration, followed by the foundry, and the final stage is of course deployment. In each of these stages, there could be different types of threats. Okay, so at the IP vendor level, there could be insertion of hardware Trojan, which is a hidden backdoor entry. How we secure against Trojan is using obfuscation. I already have given you examples of what obfuscation does. At the piracy and cloning, which is usually the case at the SOC design house, you can secure it using watermarking. You can secure that using steganography or any other type of authentication methods. At the foundry, again, you have a chance of backdoor insertion of Trojan, which is implantation of Trojan, and that could also lead to overproduction and cloning. So insertion of Trojan can be thwarted by thwarting the reverse engineering process of attack, which is again done using obfuscation. And cloning can be prevented using techniques such as, what I would say, not really prevented, you can make it a deterrent by using techniques such as watermarking and steganography. Okay, now let's look into one more application. This is an application of a watermarked FIR versus a non-watermarked FIR at RTL. Visibly, by inspecting the two circuits, one cannot say by any perceptible difference in the two circuits. So that's how we have an invisible watermarking into the circuit. Okay, so but there is a digital evidence or watermarking into one of these circuits. So for an attacker, it is very difficult to understand which is a watermark circuit and which isn't. Okay, now let me put forward one more scenario. Suppose you have some integrated circuit chips of brand X, and in that brand X, if you are able to detect a stego mark, you can probably say that that's not a counterfeit. If there is no stego mark, it is probably a counterfeit. We can never be sure, but of course, this is the way how detection of IC counterfeiting is done. In a given brand X, you can check for the authentic or original stego mark. If that exists, you can say probably it is not a counterfeit, else it is a counterfeit. Okay. Now, in case of cloning, for example, if you have a brand Y and you want to check if within that brand Y if there is a brand X IP stego mark exists. If that is so, then you will know that it is probably a cloned IC of brand X. If that does not exist, you can say it is probably not a copy. Okay. So by looking into this IC, if you are able to see a stego embedded IC and IP, you can easily prove who the original owner is. I've put in this diagram some comparison of hardware steganography with its contemporary approaches. In terms of several features, you can compare hardware steganography with hardware watermarking and hardware cryptography in terms of the abstraction level of deployment, encoding style, security protocol, designer's control, detection process, implementation complexity, and design overhead. As you can see, one of the most important thing is that the encoding style, if you see for hardware steganography, it is totally signature free. While in case of hardware watermark and hardware cryptography, you can see that it includes signature for watermarking and for cryptography it includes key-based encryption. Okay. Of course, in terms of design overhead, steganography is lower compared to watermarking and cryptography. So what are the limitations of hardware watermarking? So usually hardware watermarking is embedded in a design with the help of signature bits or signature digits, which have certain encoding rules. So we have an encoding rule for every signature digits or variable that is present. Okay. The problem is designer does not have much control over the resulting security and overhead. And the signature-based watermarking is reliant on the appropriate designer's choice of signature encoding rule as well as the digit combination. So as a result of which, what can happen is it may result into significant overhead, and it may also result into a design which isn't as secure as a designer would expect. Okay, so these are pretty much the limitations of hardware watermarking. Okay, again, getting back to hardware steganography at the encoding and decoding stages, what happens is you have a processing designer specific hardware steganography constraints which it generates from the design itself, and it creates the respective stego constraints from the design itself, and then it embeds that into the RTL data path during high level synthesis. So this is pretty much what the stego encoder system does, and as a result of that you are able to produce a stego IP core. This stego IP core, again at the decoder stage, we will try to extract the stego constraints from the IC, and then we will perform the verification to detect the steganography. This is another example of an RTL data path of an 8-point DCT before implanting steganography. You can see this is a diagram, and after implanting, this is how the diagram changes. So the red circles actually indicate the changes that have incurred due to implanting of steganography. So this is again imperceptible, and it does not incur any overhead at all. Okay, so that's how steganography is so robust. Now let me speak a little bit about IP protection or IP core protection using digital signature. So at the high level, what is the algorithm behind this digital signature? So we have an IC IP vendor watermark information, and by using that information, we will try to create a crypto hash function. We'll pass it through a crypto hash function to produce the hash digest. Usually we take SHA-512 that accepts 1024 bits and produces 512 bits, and this hash digest is then undergone through a crypto encryption function with the help of IC and IP vendor secret key. The secret key is a private key, please mind it. It is unlike encryption where you do it using a public key and then you decrypt it using a private key. In this case, you will digitally sign the hash digest using a private key, and if needed, we will do the detection part using the public key. So that's how we will embed the or generate the digital signature of the IP-IC vendor. There's one more method which is known as triple phase watermarking. This triple phase watermarking is responsible for implanting the constraints, the hidden constraints of a watermark into the design. The exciting part of this technique is that it does it into 3 different phases of high level synthesis framework. So we have 7 digits where the gamma digits is implanted at the scheduling phase, and it generates the watermark for phase 1. The second 2 digits alpha and beta is implanted at the hardware allocation phase, which is responsible for generating the watermark for phase 2. And the 4 variables small I, capital I, T, and exclamation, these 4 variables are embedded at the register allocation phase for phase 3. These 3 combined will produce a triple phase watermark, and they then get embedded into the RTL description of the hardware design. So if we have to compare digital signature versus hardware watermarking, what are the differences? So digital signature is a combination of hashing, encryption, and encoding. We need these 3 blocks, these 3 processes together to generate a digital signature. It is far more definitive, stronger proof of ownership than a watermark, and it also provides stronger detection against IP-IC counterfeiting and IP-IC cloning. Okay, it also provides better control over design security and overhead than watermark. Okay, now let's delve a little deep into the obfuscation processes. So I've put here the compiler-based transformation of the based obfuscation of the hardware accelerators that I was talking about. It could be done using 5 different phases. The first is called redundant operation elimination. Second is called logic transformation. Third is tree height transformation, resource transformation, and finally we get a obfuscated design. So what each of these blocks are basically doing is it is transforming the RTL circuit corresponding to that CDFG or data flow graph of the application. When I'm saying transforming, we mean transformation without change in any output function. Okay, the function has to be kept same, it has to be preserved. We're just changing the RTL structure in a way such that it becomes unobvious, which I was speaking of before. Let's look into one more example. This is the example of the image processing engines inside a digital camera. These could again be secured, and we have in fact secured them using obfuscation. Suppose we have these input images on the left side, and we pass it through some pre-processing block, and we arrive into something known as structurally obfuscated hardware accelerators. So the first on the top is called a blur filter. This blur filter is responsible for blurring the images. So if you see the right image of the input image, it's a blurred version of the input image. Okay, we'll do some pre-processing. This pre-processing is basically nothing but conversion of RGB input into grayscale and doing some zero padding so that we can keep the output matrix of the same size as the input matrix. Okay, and the post processing is nothing but conversion of the double data type into integer and then converting back into an image form. The second one is known as sharpening filter hardware accelerator. The third is vertical embossment. The fourth one is horizontal embossment filter, and the last one is lapless edge detection. So these are the 5 different hardware accelerators from image processing that we have designed in our lab. Few more examples from medical domain. For medical imaging systems, we can also develop secure JPEG compression hardware. As you can see, these the pixel intensity values of these images are generated through the obfuscated JPEG compression hardware. These are CT scan images of different patients taken from some publicly available database, and you can see our hardware, secured hardware, was able to generate the accurate pixel intensity values of these medical images. Uh, this is another example of an obfuscated design of a fault secured FIR filter. Okay, this is the obfuscated design, and in the next slide you can see the non-obfuscated DSP structure. As you can see, there's a massive difference in the structural topology of the two circuits, although the output remains preserved. Okay, now moving on, I'll talk a little bit about logic locking or logic obfuscation. If you see the flow diagram here, you see basically the flow diagram is as follows. You have an application from which you can generate the original netlist of the IP core, and once you pass it through some logic locking algorithm or functional obfuscation process, we can generate the lock netlist of the IP, which can then be converted into or integrated with the C device ICRTL netlist, and then we can convert that into a GDS2 through layout synthesis followed by fabrication to convert it into a mask and then into a non-functional IC. Then further it goes into the packaging to produce an IC activation, and finally we have a market ready functional IC. Each of these stages from the RTL netlist, GDS, masking, non-functional IC, functional ready IC can all be reverse engineered to obtain a locked netlist. Okay, so the goal of the attacker is to somehow get the locked netlist. So they can reverse engineer from each of these 5 stages marked in red. Once they have the lock netlist, they can use the lock netlist along with the functional IC to launch certain forms of attacks known as key sensitization based attacks to produce a deciphered netlist. So the goal is to finally produce a deciphered netlist. So the inputs to get to that deciphered netlist is to know the key sensitization attack, to get the locked netlist, which can be done using reverse engineering, and to also get hold of the functional IC, which is market ready. Okay. So formally defining reverse engineering, it is a process of gaining the complete understanding of the functionality, design, and structure. And RE can be used for any dishonest intentions such as overbuilding, piracy, or counterfeiting, or even insertion of malicious hardware Trojan. Let's look into sensitization attacks, which I was talking. These could be of different types. So key sensitization becomes very easy if the gate structure has one of these three properties. For example, the first one is isolated key gates. If there's no path between K1 and K2 in the first figure, then they become isolated key gates, and it becomes easier for an attacker to sensitize the value of K1 to the output by applying certain input combinations. The run of key gates, which is the second one, is a certain topology where the key gates are connected in a back-to-back fashion, and it also increases the possibility of correct key combination, which is again not good for the designer's perspective. And third is mutable key gates or concurrently mutable key gates. What can happen is if two or more key gates converge, but they have no common path between them, then it becomes easy. For example, if you apply I6 to 0, then we can easily mute K2, and therefore K1 can be sensitized to the output. So using this key sensitization based attacks, an attacker can perform IP piracy and Trojan. They can perform removal attack. Removal attack means to remove all the locking gates from the circuit at the netlist level, so that it just becomes like a normal unlocked netlist, a normal netlist. And they can also perform SAT attack, which is to identify a way to identify distinguishing input output pattern, so that it can be used to eliminate all the wrong key combinations till no new ones can be found. So what's the way forward? How can we stop it? We can stop it using functional obfuscation. So one of the ways that we have devised in our lab is to produce a technique where you not only produce the output in based on the input values of 2 bits, but to produce output based on input values of 8 bits. So that becomes very complicated and complex for an attacker to unlock. Okay. So let me show you a structure. So here you can see this is known as IP core locking block. You have K1 to K8, all the 8 combinations of the input bits has to be correctly applied to unlock a single bit of the output. Okay, so this becomes extremely complex. And these ILB blocks are just designed using basic combinations of AND, NAND, NOT, XOR, and NOR. So they do not produce any extra large overhead on the system. So one such application that we have designed is for a 4-bit FIR. As you can see, the red blocks are the ILBs, which I was just talking about in the previous slide, and they have 8 key bits for every output decryption. And in totality, we have so many inputs, and we have a combination of AND, OR, XOR, XNOR, and so on. So once synthesized, this all become converted into primitive gates, and it becomes indistinguishable to an attacker, so that he fails in removing the ILB locking gates or ILB locking blocks. One of the other ways to also handle it is to augment a custom AES architecture at the input, where partially some of the key values will be generated through the AES structure. So the ILB blocks will not have a predefined template. So ILB template will change based on the output of the AES structure. ILB key values will change based on the output of the AES structure. And for knowing what the AES structure is, the person has to know the value of the fixed secret key of the AES, so which is usually 128 bits. So that becomes difficult for an attacker. So this is another way to thwart the removal and SAT. It can also be done using SHA. So SHA can also be used in place of AES. So SHA can again be made to convert certain outputs, which can again be used for generating the ILB inputs. And based on that, at runtime, there will be different outputs produced, and the ILB structures will also be reconfigurable. As a result of which, the attacker will not be able to gauge what the fixed structure is, and will be unsuccessful in removing the ILB structure from the gate level netlist. So I would like to conclude the talk today. As you see, the future of C system and IoT design or autonomous vehicle, there is a trade-off between energy and security. I have been speaking so much about security today, but at the end of the day, you cannot just apply security protocol or algorithm in a design without being able to balance the energy or power. So therefore, the comprehensive system will have a well-rounded design space exploration technique that encompasses security protocols as well as takes into account the power versus delay trade-off. Thank you so much.
Thank you, sir, for this wonderful session. And now I think we can move towards the doubt session. Like if they are having any doubts regarding security, or
Sure.
unmute their mic and they may just ask the questions, or they may just message in the chat box any doubts, or else we can conclude this session. If students are having doubts, let us know.
Please feel free to ask me questions if you have. If any student is thinking to work in this area or wants to explore, please feel free to ask me some fundamental questions. It doesn't matter. So, Akash, I have some feedback for you. I just wanted
Yes, sir.
to I just wanted to know the main motive of doing a webinar on hardware security and IP core protection. This probably the topic was already predefined, right?
Hello, sir. I didn't get you. Hello.
Yeah.
Can you
Can you
just
hear
say
my
once more?
voice?
Hello.
Can you hear my voice?
Yeah.
Yeah, I wanted to just find out what was the motive of conducting a
Yeah.
webinar on
Hello.
hardware security.
Okay. So actually, the thing was simple. Actually, we were planning. We have actually planned a series of webinars for the students,
Hmm.
uh, and our aim was to touch maximum fields related to computer science, so that the are having the doubts regarding those fields they can ask to the people. So we were seeking for the people who have expertise in these fields. Like we have coming webinars related to threat modeling and in quantum computing and so on topics. So we just wanted to cover each and every stream in computer science, so that the students who are going for their higher study or anything their related topics, so they may just cover up their.
Okay.
So that was the main motive regarding the webinar.
Okay. Perfect.
Okay, so I hope so the students are not or the participants are not having any doubts. So I guess we can conclude the session, or if there is anything you want us, or you wish to tell us something from your experience, so it will be much better for you us.
Yeah, I mean, see, look, any prospective student or any researcher wanting to venture in this area in future, higher studies, whether it's a master's program or PhD program, my only suggestion to all of you, whoever wishes to work in this area, would be to keep your mind broad in terms of interdisciplinary approaches. We have come to a stage where just knowing a single topic, just knowing AI, just knowing machine learning, or just knowing quantum computing will not fetch you productive results in research. For doing research and taking research to the next level, students should, or any prospective researcher should have knowledge on multiple fields or multiple disciplines. So therefore, anybody working wanting to work in hardware security should have knowledge on VLSI aspects, on CAD algorithms, on high-level synthesis, on digital systems. Should have knowledge on optimization. Should have knowledge on cyber security, cryptography. So there are so many things. Should have knowledge on some application domains such as machine learning, image processing. So I would really suggest that you please start reading uh, multiple things at the same time so that you can collate and augment them together to define a very serious, novel, and effective research problem that nobody has solved. And that's how you can actually flourish and prosper as a researcher in your field in the future during your master's or PhD programs. That's the only suggestion I have. Akash?
audible?
Yeah.
Yeah, okay. Sir, actually, I had a question. Like, it would be have better if you could suggest us a blog site or something relevant to it where we can find the articles regarding hardware security or something which you refer in your daily day
See,
or something like that
Akash,
relevant to that.
I'm not sure how easy for you it would be to procure the books that you mentioned right at the beginning.
Okay.
You may look for it online. These are all readily available in Amazon, and different publishers are putting it up on their website. You can please procure through your library, through your university library, and you can read up the stuffs. It's all available there, and I think it will be a one-stop
Okay, sir.
complete writing of all what I said. Okay, I
Okay,
think
sir. Okay,
you
okay,
really
okay.
don't need to refer to much blogs because I do not trust the authenticity of the blogs that much. These are usually written by many people who are not really experts. So I really do not would not recommend you to go to any blogs to read about hardware security.
Okay, sir. Thanks a lot. Thank you.
Okay,
So,
okay,
sir,
thank you.
we can actually wind up the session. Okay,
Sure,
sir. Thanks a lot for giving
thank
such
you.
webinar on hardware and IP protection. And it was a glad for having you in for a presentation. Thanks a lot, sir.
Sure.
Thank you.
I've been receiving some comment from participants to share the PPT. I just received some comments that they're interested to look into the PPT of the. So I will share that to you.
Yeah, sure.
You are
I will
welcome
just
to
share up
participate.
the PPT. Yeah, sure. Just send the email in the comment box or in the message box so that I can just copy down the emails who all require, or else I will just forward it to the participants who have registered. So it will be better for me to just those who are interested for the PPTs. Please write down the or please mention your email IDs in the comment box.
Right. Akash, do you have the? You will have the video recording, video audio recording of this talk, right? You can please share the link with me for that.
Yes, sir. We
Okay.
will be uploading you within 1 hour. Actually, so you may
Yeah,
just
you already
upload in the
put that
platform
up on the
whichever you
group,
think so.
so that's why I'm looking for that. Okay.
Okay, sir, it will be glad if you could send me the PPT
Sure.
via mail so that I can just send.
I'll send you that. I'll send you in
Okay,
next like 2 3 minutes.
okay,
Okay.
okay. I will share the PPT as well as the recordings to the participants. Thank you, sir. Thank you for the webinar. Thank you, sir.
Okay. Thank you, Akash.